Hello and welcome to the first lecture of week 12 of the course Introduction to General Relativity. This is the final week and we focus our attention towards using general relativity to describe the structure and dynamics of our universe at the larger scales, that is cosmology or relativistic cosmology. Now this lecture will be close to 1 hour in duration and will be split up into two parts or two lectures on the NPTEL website, namely lecture 63 and 64. Now, in contrast to the Schwarzschild solution of general relativity which we studied earlier, which was a vacuum solution, that is, the source stress tensor was set to 0, the cosmology would require us to solve the field equations with matter-energy sources turned on, as we will see in the universe. For example, normal baryonic matter is radiation, dark matter, and dark energy. Now, solving Einstein field equations then amounts to working out the form of the metric, as we've seen. And what we have seen before, that while solving for the Schwarzschild metric, the solution is greatly aided by having a suitable metric ansatz, which was guided by the symmetries of the problem. Now, this lecture is titled Cosmology Part 1, Kinematics, where we will exploit symmetry and symmetry alone of our universe at the larger scales, namely spatial homogeneity and isotropy, to constrain the form of the spacetime metric or interval to a form which is called the Robertson-Walkermetric. And we will discover that certain features or observations about our universe, namely the Hubble law for recessional velocities of galaxies and the possibility that the observable universe is finite, that is, the existence of a cosmological horizon, will naturally follow from this form of the metric, even without solving for the metric by plugging it in the field equations. That is, without involving any dynamics. As for references for this lecture, I will suggest the following sources. The first is the set of TASI lecture notes by Carolyn Troughton, available for free on the archive, the Astrophysics archive in particular. Sections 2.1 and following pages is where you can find the relevant material. And this has a significant overlap with the material in Carol's lecture notes in general relativity, which is also available for free, chapter 8 and the following pages. The second reference is Weinberg's text. The relevant material can be located in chapter 14, following sections, 14.1 to 14.3. In these pages. The third reference is Barbara Ryden's text, Introduction to Cosmology, which is a popular cosmology text at the advanced undergraduate level, and will also contain the relevant material in chapter 3, following sections, and these pages. Daniel Bauman's lecture notes on cosmology, which was prepared for part 3 of the Tripos at Cambridge University, which is an advanced master's degree, also contains the relevant material, chapter 1, these sections and these pages. Now, this resource is available online for free. Finally, as per usual practice, the lecture notes for this lecture will be posted on the NPTEL/WEM website for your reference. All right, let's look at our agenda today. So the first item of agenda is to look at the certain observations we make while looking at the universe at the largest scales, namely homogeneity and isotropy, which is packaged into something which we call the cosmological principle. We will look at the implications of this for the spacetime metric, which we can write down for this. And that would lead us to the second item, which is called the Robertson-Walkermetric for the universe, which can be written down, as I've mentioned before, just on the basis of the symmetries. And then we will see some consequences of this form of spacetime metric for the large scale of the universe. Namely, it will lead to something called Hubble law for the recessional velocities of galaxies and the redshift scale factor relation. All right, which the redshift scale factor relation might be a bit unknown to most of you, but it relates the redshift of the light we get observed from a galaxy to time at which this light was emitted. All right, without further ado, let me begin the lecture. First item on the agenda, as I said, is to take a look at the universe at the larger scales, and that will lead us to something called the cosmological principle. Now, as I said, we can apply general relativity to study the structure of the universe at the larger scales. And the larger scales are enormous, and so big that the galaxies, which we usually consider to be very large, will appear as point particles. And if we study that, gives us the branch of general relativity, which is called relativistic cosmology. Now, at the larger scales, I need to quantify this. What do I mean by larger scales? Larger scales, I mean a few hundred megaparsec. Remember, 1 parsec is 10 to the 16 meter. So a few hundred megaparsecs is maybe 10 to the 18 or 19 meters, which is an enormously large distance. Now, if you zoom out to such large scales of the order of a few hundred megaparsecs, the universe appears to be isotropic. That is, if you look in any direction, it appears same. Okay. Two, typical observers. I'll define typical observers at the moment, but this is a bit of a self-circular logic. A typical observer is of those which would appear to whom the universe would appear to be isotropic. And the biggest proof of this isotropy comes from the observation of the CMB, which is the cosmic microwave background radiation. Most of you perhaps know that if we look at the sky, then the sky seems to be full of this uniform microwave radiation, which is called CMB. And the uniformity of the CMB in any direction is a feature which we call isotropy. Apart from that, one can look at the distribution of galaxies or matter in the universe. And at the larger scale, of course, if we look at distribution of matter at small scales, for example, on Earth or in the solar system, we can see it's pretty much lumpy. It doesn't look the same in all directions. But you have to zoom out to large scales when these non-uniformities are smoothened out, and we get to see a very uniform and isotropic, that is in all directions same. Okay, so SDSS is the Sloan Digital Sky Survey. People have looked at the data, and if you zoom out to very large distances, the distribution of galaxies and matter seem to be same in any direction. Okay, so the isotropy of the universe at the larger scale is a fact, is an observational fact. By the way, I need to mention that the Milky Way, or Earth, is not a typical observer. In fact, it has a peculiar velocity of 600 kilometers per second with respect to the typical observer. That is the rest frame of the CMB. All right, so as a result, if you look at the CMB from Earth, you see a pattern which is known as a sort of anisotropy in the CMB, which is called the dipole anisotropy. And that we understand is because Earth, or the Earth-bound observer, is not a typical observer. It is moving in the rest frame of the CMB with some velocity. As a result, there is some anisotropy in the direction of motion and in the direction opposite to the motion. Okay, so Earth, or Milky Way, is not a typical observer. So the next observational, or I should say philosophical principle is the Copernican principle, which says that there is no preferred location, or there is no center of the universe. So if there is no preferred location, every location is similar in stature, or in other words, we say that the universe is spatially homogeneous. Okay, so this is the Copernican principle, which most of you know from the early days of astronomy. People thought the Earth was the center of the universe, and then Copernicus came along and said, no, Earth is not really the center of the universe. In fact, there is no preferred center or location in the universe, and all locations are more or less equal. So Copernican principle tells you that the universe is spatially homogeneous. And then if you combine the isotropy with the fact that the isotropy of a typical observer with the fact that any location should see this, we are led to something called the cosmological principle, which says that at the larger scales, again, larger scales by larger scales I mean a few hundred megaparsecs, the universe is spatially homogeneous and isotropic. Okay, all directions look the same, and every location, the way the universe appears is also the same. Now, conversely, if we assume that you're in a space in which every point, at every point the space appears to be isotropic, then automatically this would imply homogeneity. Okay, so this I will leave as a homework exercise to prove. If you consider 2 or 3 points on space, and if all directions appear to be same at each point, so at each point if space appears isotropic, then you can show that this implies that space is also homogeneous. Okay, I will leave this as an exercise. Now, as a result of spatial homogeneity and isotropy, one can write down an ansatz or a form of the metric on constant time, that is spatial section, because space appears homogeneous and isotropic, right? There is something called also the perfect cosmological principle, which says that the universe is not just spatially homogeneous, but it is homogeneous in time as well. We are not talking about that. The perfect cosmological principle leads to a different model of the universe, which is called the steady state theory, in which it is difficult to explain the CMB, so it has fallen out of favor, and we use the cosmological principle in which the universe is only spatially homogeneous. Okay, so spatial homogeneity and spatial isotropy will constrain the form of the metric in spatial sections, that is constant time section. Okay, so let's write down the metric on the constant time section, which is called the spatial section. And isotropy would mean it must have spherical symmetry. So then, just like we did for Frobenius, using Frobenius theorem, that then one must have foliations in which the foliations are spheres, 2 spheres. So we use 3 coordinates, rho, theta, and phi. Remember, this d omega 2 squared is nothing but the metric on the 2 sphere. So we have foliated spatial sections into spheres, and these leaves or foils are given by distinguished by this coordinate rho. Okay, so this is just Frobenius theorem in action, which we already used while deriving the Schwarzschild solution. So isotropy and homogeneity, or at least from isotropy, we can write down this form. Okay, so I'm sorry about that. This is not using homogeneity, just using isotropy, we can write this form. And then we can wonder what this unknown function f of rho is, right? So what can we say about f of rho? Okay, and we know we haven't used the spatial homogeneity property of the universe, so it must be constrained or fixed, determined by homogeneity. But even before that, even before we use homogeneity to constrain this, something is completely obvious, is that if you have a metric of this form and you compute the Ricci, the Riemann and the Ricci curvatures respectively, one can show that at rho equals 0, there is a conical singularity. Okay, rho equal to 0 is a conical singularity, that is the curvature diverges, unless you choose f of rho, to be such a function that in the rho vanishing limit, this must be proportional to rho, or equal to rho, not proportional, equal to rho. So f of rho, if it's an analytic function of rho, you can expand in the power series. So it will be something like rho plus some coefficient a rho square plus b rho cube, so on and so forth, so that when rho goes to 0, the leading behavior is equal to rho. F of rho is equal to rho when rho goes to 0. All right, so this much we can tell even before we see, we look at the constraints which homogeneity brings in, that f of rho must be equal to rho as rho tends to 0. Okay, so now let's look at the constraints of homogeneity. The first thing we can observe is that rho equal to 0, we assume that to be the origin. But in a spatial homogeneous manifold, any point can be chosen as the origin. So please bear that in mind when I go to the next slide, that I can choose any point to be the origin. All right. Metric on spatial sections. Now we use homogeneity. So what I have here is this diagram. You can see this set of points O, A prime, B prime, P prime. These are all points on the equatorial plane, that is theta equals pi by 2 plane. Okay. So because it is on theta equals pi by 2 plane, each point is given by certain coordinates, which are rho and phi coordinates. For example, the origin, I can take rho equal to 0. I can take this to be rho equal to 0. And as you know, phi coordinate is not well defined at rho equals 0, so we will not specify phi. Other points like P, I have chosen such that the phi axis is here. Sorry, not the phi axis, the x-axis is here, or this is the phi equal to 0 direction, and then as you move up, phi increases. Okay. All right. So any point can be taken at the origin, as I've mentioned here. Just for convenience, I've taken O to be the origin, but as we do the analysis, sometimes I'm going to take P to be the origin, B to be the origin, or even this point A to be the origin as well. Okay, so this is a point at the corner. All right, and this is a triangle in which this angles gamma, and so gamma is here, and beta, and these are very small. Okay, just for purposes of illustration, I have exaggerated them, but this is actually a very thin slice, thin triangle. So these angles gamma and beta are both very small. Okay. Now, with that in mind, let me ask the question: what is the length of the segment BB prime? So BB prime, which I have shaded in red. What is the length of this BB prime? And you're going to say, okay, I can use the metric because I know the metric on spatial sections. I know the I can use the metric to write down the difference between the distance between B and B prime, and that will give me some notion of that will give me the length of BB prime. Now, if you do that, you can do it in two ways. First, if you regard O as the origin, and then the rho coordinate for B and B prime will be given by rho plus x. Let's say B is such that it's so this is rho equal to 0. This point P is at some value rho, and then A is at twice of rho. Okay, so P is kind of exactly the midway between O and A. All right, and then B is somewhere between P and A, so it's a bit more than rho plus x. Okay, the rho coordinate is rho plus x, and if we do the rho coordinate, and this is the angle from the origin, so we can immediately write down that, well, B and B prime almost have the same rho. B and B prime have the same rho, so the only thing that's varying is phi. So this part won't contribute. F of rho times whatever is this quantity, but theta is fixed, and sine theta is 1. So this is f of rho times d phi. So this is what I've written. D phi is the angle distance between the lines OB and OB prime, and that is gamma. Sine gamma is equal to gamma because gamma is small. And then f of rho is at this point, and this point rho is almost the same, which is rho plus x. Okay, so f of rho plus x times gamma. This is the length of the line segment BB prime. Now I can evaluate this same line segment, the length of this segment, another way. First, I can write BB prime, the segment BB prime, as the sum of the segment QB prime, or BQ, this part, plus QB prime. All right, I can write it this way as well. And then, as I said, any point can be chosen to the origin. to determine BQ, I can choose A to be the origin, and then compare with respect to A, the row coordinate of this point is rho minus x, because A is twice a rho, and this is rho plus x. So the difference between them is rho minus x. So if I choose A to be the center, according to this, the radius will be f of rho minus x times the angle sine gamma. Again, this is equal to gamma. So this is what I have. F of rho minus x times gamma. And here I'm regarding A to be the center. Now, we also have to evaluate QB prime, this segment. The way we evaluate QB prime is by regarding P as the origin. Alright? If P is the origin, the value of rho at P prime should be set to, not P, P prime is the origin. So P prime must be set to rho equal to 0. This is 0. So then this point B will be just x. Okay, if this is 0, then the row coordinate of B prime should be x, because initially when O was the origin, this had coordinate rho, and this rho plus x, so the difference is x. So this is of length f of x, and then sine of angle beta is beta, because beta is also small. Okay, in the linear approximation, we can write this. So the segment BB prime, we evaluated. Let me just erase these things so that it reduces clutter. So BB prime we have evaluated in 2 ways, and we get this equation as a result. And we can perform a similar exercise for the segment A prime. Okay, this blue segment A prime. Now this can be evaluated again in 2 ways. First, you regard O as the origin, and then this radius or this distance is f of twice of rho, because the point A is labeled by twice of rho. So twice of rho times sine gamma will give you the length. And sine gamma is gamma, so because gamma is small. Similarly, you can regard P prime at the origin, and then A prime, the segment, can be thought of as taking this radius, which is, so I'm regarding rho as rho equal to 0 now, so twice of rho will be just rho, f of rho times sine of beta, or just beta, because beta is small. So for the segment, blue segment A prime, I get this equation. F of twice rho times gamma equals f of rho times beta. Now from these 2 equations, I can evaluate the ratio of beta to gamma. And beta to gamma right now, is the only constraint is that they are small. I'm not constraining them in any other way. So the ratio of beta and gamma I can evaluate from both equations, and I equate them, and I get this relation. All right? So this is equal to beta over gamma. All right, once we have that, we can take a limit, x going to 0. The reason we take this limit is because we know when x goes to 0, to avoid a curvature singularity, f of x must go over to x. Okay, so this will become x as the limit x goes to 0, and then we can recognize this is nothing but derivative, or in fact twice the derivative. So this is what I have here, the derivative. And this 2 can be brought over to the other side in the denominator, which we have here. By taking this limit, we get a differential equation for f of rho. So f of rho, which was unknown, homogeneity gives you a differential equation which f has to obey. And once you solve this, you get to know the full metric. Okay? So isotropy gave us a form in which f was unknown, and then homogeneity led us to a differential equation for f. If we determine this, we're basically done. Now it can be shown, and I've left the proof as a homework exercise. Please work it out, solve this differential equation, that there are only 3 possible solutions up to a scale. I'll mention what I mean by up to a scale. The 3 solutions are f of rho is equal to rho, f of rho equal to sine of rho, and f of rho is equal to sine hyperbolic of rho. Now, when I mentioned that these are three possible solutions up to a scale, what I mean is that these are not the only solutions per se, but if you take a solution and f of rho, then big of rho, which is defined so, lambda times f of rho by lambda. So the argument instead of rho is now rho by lambda, but lambda is an arbitrary constant. And if you multiply this f of rho by lambda times lambda, that is also a solution. This is what I mean when I say that the solution is up to a scale. So the unified form for the metric for using all of three cases, unified in the sense that I'm covering all three cases at the time, is given by this. The spatial section metric is d rho squared plus f kappa squared rho times d omega squared. The d omega squared is nothing but the metric on the two sphere. And f of kappa of rho can take three different not values, but three different forms, depending on the value of kappa. So kappa is a discrete, assumes discrete values. It can take three values, plus 1, 0, and minus 1. And when it's plus 1, the solution is sine rho over r times r, where r is a constant. So this is what I mean, the three possible solutions up to a scale. So this scale r is kind of arbitrary. And these solutions, I've chosen r to be 1, but you can take it to be anything. And then rho, the solution, if you do a scale r times f of rho by r, then the r will cancel out. So the solution is the same, even if you scale it. And finally, the sine hyperbolic, I should divide by rho and then multiply it. Divide the argument by rho, r, and then multiply by r. Okay, so this is the third solution, which I'm distinguishing by kappa equals minus 1, which is distinguished by kappa, and each case also has this constant r, which is a continuous constant. I mean, it doesn't have to take discrete values, it can take any arbitrary real value, 0 to infinity. What are the significance of these two numbers, kappa and r? And their significance becomes obvious when we compute the curvature. In particular, if we compute the scalar curvature, or the Ricci curvature, Ricci scalar, then it turns out that the Ricci scalar is constant. At any point on the spatial section, if I compute, it is constant and is given by 6 kappa over r squared. So kappa actually determines the sign of the curvature, whether it's positively curved, or negatively curved, or no curvature at all, like flat. And r sets the scale of the curvature. Okay, the bigger the r is, the smaller the curvature is. All right. So now we know there are special manifolds which are called maximum symmetric spaces, for which the Ricci scalar is indeed same throughout or uniform. And in fact, these three solutions are three maximally symmetric spaces, which we can also deduce by reminding ourselves that there are 6 scaling vectors, 3 for 3 translation, because we are in a 3-dimensional plane or 3-dimensional spatial section. So there'll be 3 translational directions, and then there'll be 3 rotation as well because of isotropy. So 3 plus 3, that gives you 6 scaling vectors. So in 3 dimensions, we know 6 is the largest number of scaling vectors you can have. So these spaces, these 3 solutions correspond to maximally symmetric spaces. Okay. And we also remember, if you remember the discussion we had back when we were talking about scaling vectors, that these maximal symmetric spaces are only three of them, especially if you're looking at Euclidean sections, which we are, then these 3 maximally symmetric spaces are the sphere, the Euclidean plane, and the hyperbolic space. Okay. Although we did not give a proof at that time, the proof can be obtained here by following through this exercise. And you can show that there are only 3 solutions up to a scale. And that kind of completes the proof that the maximally symmetric spaces are the sphere, the hyperbolic space, and the Euclidean plane, or hyperplane, 3-dimensional Euclidean hyperplane. All right, now there are certain alternative forms of the metric used in the literature. Now, one straightforward thing one can do is, in this metric, which we have distinguished in purple fonts, this f of k, f sub kappa of rho, we can call this to be r. So capital square will be called r square. We can do such a coordinate change, a diffeomorphism, and in those coordinates, the metric looks something like this. So this you can recognize the usual form, r squared d omega squared, where r is the radius, and then the radial part picks up a denominator. And it is also more common, especially in a lot of textbooks, including Weinberg's, is that one can scale this little r by this big R. So define a new coordinate. So replace everywhere where you have little r by big R times little r, and then you get this metric. Okay. In this metric, if you replace all the little r's by little r times big R, where big R is a constant, then you get this overall constant of r squared, big R squared, multiplied by this. Now, one thing you must notice, although we're using same r in the upper form, little r does have dimensions. It has dimensions of length. In the lower form, little r is actually dimensionless, as you can see very well, because the metric is length squared. We already have a factor of length squared here, so everything inside must be dimensionless. So that tells us r is also dimensionless. So if you're using the second form, please be careful that r doesn't naively give you doesn't have the dimensions of length. It is actually dimensionless. One can also use Cartesian coordinates. It's also commonly used. In Cartesian coordinates, what you're starting with is, because these are maximally symmetric spaces, three-dimensional maximally symmetric spaces, they can be realized as hypersurfaces inside R4. Okay, all three cases can be thought of as some kind of hypersurface lying inside R4, and they're given by this relation, except for kappa equal to 0. This R4, points on R4 are given by x and z. These are the 4 coordinates, and x vector is actually a 3-dimensional vector, so x1, x2, x3. But in R4 we need 4, so in addition to x1, x2, x3, we also need a z. x3. All right. So we have it here, and then we insert it, and we get a surface inside R4. If kappa is +1, you get a sphere. If kappa equals -1, you get the hyperbolic space. And in this, and from that, you can from the metric of R4, one can always write down the pullback metric on that hypersurface. Please remember the pullback metric, how we constructed that using the notion of the pullback. So the pullback metric is what I've written here. Now, if you set kappa equal to 0, you indeed get the R3 metric. So although this equation, in the hypersurface equation, you cannot put kappa equals 0. Actually, you can put kappa equals 0. It doesn't matter. You can't actually. So that will give you, in fact, that gives you z equals +1 or -1, which are a double plane, but we only want one. So maybe you have to choose one of the solutions of kappa equal to 0, which is z equals +1 or -1. And for regardless, for either of them, if you either choose +1 or -1, you're going to get the Euclidean metric as the induced metric or pullback metric on these hypersurfaces. So these are the 3 commonly used forms. Either you can use rho theta phi, or you can use r theta phi, or you can use x1, x2, x3. All right, so the metric on the spatial section is now completely fixed. Homogeneity and isotropy has completely determined the metric. Now we have to ask, okay, now how does we bring time into play here? Because the universe has both space and time, and in general relativity we have to write down the space-time metric, or the space-time squared interval, rather than just the spatial section. So spatial sections, one way of doing this we'll start from a general metric, and we will make sure that when the time dt is equal to 0, then the space-time metric must reduce to the spatial metric, right? This is one way we can constrain the form of the space-time metric, and let me write down. So Before we do that, actually, I just want to introduce some notation. The spatial metric d sigma square, I will write using whatever coordinates you want, dxi, dxj, some abstract coordinates, and gamma ij would be the component. Okay, so gamma ij I will use to imply the metric on the spatial sections. Okay, all right. Once we have this, now let me go back to the point I was mentioning, that if I know the metric on the spatial section, how do I write down the metric for space-time interval? And that will be given by this form. As you can see, there is a dt square, which is the time, comes with g00 as a function of time. Actually, it can be, let's say the dependence is not indicated, it can be a function of t or, and then g0r, dt dr terms will be turned on, and this is the metric coefficient. And then we will have some coefficient for this d sigma, which should also be a function of time. Now these should be functions of time, because if they become functions of spatial location, then the universe will not be spatially homogeneous. So they cannot be functions of location, okay? And also for similar reasons, because of isotropy, we have to rule out terms like d theta, dt d theta, and dt d phi, because they're linear in the angle change theta and d phi. So they will reverse sign when I go clockwise d theta or anti-clockwise d theta minus. So we don't want the points which we go clockwise direction or anti-clockwise direction to look any different, because that would be not compatible with isotropy or spherical symmetry. So we will drop the dt d theta, dt d phi. They're not compatible with spherical symmetry. dt dr can be there, and r has radius, has nothing to do with spherical symmetry. So this is the form of the metric. Metric coefficient must be a function of t only. They cannot be a function of r, because that means if I go to larger radius, the universe looks different, which is not a good thing. It just tells you that then you don't have homogeneity of time. Okay. Now, to further constraints, I will choose something which is commonly done in cosmology, in fact in general relativity, which is called the synchronous gauge, or the synchronous coordinate system, or synchronous reference frame. Okay. So in this reference frame, it will turn out that g0r is equal to 0, and g00 equals -1. Or if you're using an SI units, then you should put -c squared. Now, how do we get the synchronous frame? For this, let me illustrate how do we do this. So let's say we have the universe at some constant time, t equal to 0. This is the spatial section. And let's say, let me look at a point which is rho equal to 0. And so rho equals 0. This is the origin I've chosen. And let the universe at certain different point of time be given by a spatial section, which is like this. T, which is positive. Universe at a later time. Now, we can ask, what is the point, which point on this new slice corresponds to rho equal to 0? And one way of doing this is you draw a normal vector to the initial slice at t equal to 0, and you continue this normal, which is orthogonal, and you go to continue the normal till you intersect the t greater than equal 0 slice somewhere here. And that point, you choose to have same rho equal to 0. And you do this everywhere, not just for rho equal to 0. You start from somewhere else where you have rho theta phi. And again, you draw normal vector and continue the normal and see where it intersects on this later time slice, and make the coordinates of that point rho theta phi. If you do that, rho theta phi, spatial coordinates, and the time coordinates will be t. So this is rho equal to 0, theta phi is of course not defined at the origin, so I'm not writing them. this point is rho equal to 0 and t equals 0. And the point where the normal meets, we will call that rho equal to 0, but t non-zero. Similarly, rho theta phi and t equal to 0. If you take the normal, wherever it intersects, we will call that point rho theta phi, comma, t. Okay, those are the coordinates of this point. Now, if we do this procedure, then this t direction, where t is changing, is actually orthogonal to the constant time sections. So that's why this term will vanish. Okay, this term will vanish. Del t, this vector is normal to the constant time section, constant time slice. Okay, so by choice, we can always do that. This is how we can define our coordinate system. This is completely up to us, and general relativity allows us the freedom to choose coordinate system. In particular, we are choosing the time here. Remember, this is defining the time. So further, as I said, what is the time elapsed in this? That we will take to be exactly equal to dt square, not g00 times dt square, but just dt square, which is the same as saying that I'm choosing g00 to be minus 1. Okay, so g00 is chosen to be minus 1. So this two choices are together called the synchronous gauge. So then if we do that in this metric further simplifies, and it is said to be of the form written down by Robertson-Walker, or the Robertson-Walkermetric. So as you can see, ds squared is minus dt squared now, and this term is gone, and we just have a of t squared times the spatial section metric, which is completely determined. So this form of the metric, as I mentioned, is called the Robertson-Walker metric, and they were independently arrived at by Robertson and Walker sometime in the mid-1930s, and they said just purely on the basis of isotropy and homogeneity. And d sigma, again, I'm going to use this abstract notation. D sigma I've written here as gamma ij dxi dxj. And in the literature or in books, you will see that this combination of a squared t gamma ij, this combination together is sometimes written as little gij, okay? The full space-time metric component, gij, spatial component of the full space-time metric, okay? Arrived at the Robertson-Walker form of the metric. And it has three unknowns, of course. This scale of curvature of spatial section is undetermined. The sign of curvature of the spatial section is undetermined. And of course, this function a of t, this function of time, is also undetermined. This is called the scale factor. And more about this later. Now, the spatial coordinates r theta phi or rho theta phi, whatever you're using. If you're using Cartesian, you can have x1, x2, x3. These are called co-moving coordinates. And any observer whose co-moving coordinate remain fixed, remember that diagram we made before, we have a spatial section, spatial section at later time, and let's say this is rho theta phi, dot, dot, dot. And then this is the t direction, and intersects to this point, rho, dot, 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 same coordinates, but different time. This is t equals to 0. Okay, so the trajectory one gets by varying just t and keeping rho theta phi fixed turns out to be a geodesic. You can show that the geodesic equation is solved by this t varying, but rho theta phi unchanging. So these, because they are a time-like geodesic, they can describe freely falling observers, okay? And these observers, for whom the co-moving coordinates are not changing, are the typical observer. This is now we can technically define the typical observer. Typical observers are those for whom the co-moving coordinates are not changing with time, okay? Now, it is also true that little t, this time coordinate, is the proper time of co-moving observers. That is pretty obvious. And the way we write down that if we take for co-moving observers, because the co-moving coordinates are not changing, this is 0. And then the proper time, which is defined as minus tau square, the same as minus dt square. So that means t I can identify with the proper time of co-moving observers. Okay, this time coordinate little t is same as the proper time of co-moving observers. And you don't have to take any special location because the universe is spatially homogeneous. You take any point and the proper time of the observer who has constant co-moving coordinates will be the same as the little time little t. Now this is contrast with the case of the Schwarzschild solution, in which the Schwarzschild time coordinate little t was actually same as the proper time of clocks at infinity, observers at infinity. But here, unlike in this case, in the case of the spatially homogeneous and isotropic universe, this actually corresponds to any observer whose co-moving coordinates are not changed. Such observers are called typical observers. So the proper time of co-moving observer, and it is also, this little t is also referred to as cosmic time or cosmological time in the literature. And this function a of t is called the scale factor. Okay, it measures how the distance between two co-moving observers on the spatially homogeneous isotropic universe varies as a function of time. So let me draw this picture once again. So we have got the spatial sections at two different times. So this is t equal to 0, and this is t greater than 0 slice. And let's say we take two co-moving observers, that is, let's say this is rho equals 0, some theta phi is undefined, and this is some rho theta phi. That. And now we construct the normals, which meet somewhere here, meet somewhere there. Now, a of t determines how large this distance is compared to how this distance is. So at a later time, the physical distance between them will be changing because a is a function of t. And this a of t keeps track of that. It measures, given the fixed co-moving coordinate, how the distance between them is changing with time. It can decrease or increase depending on the matter of the universe, matter the energy distribution of the universe. But the idea is, you took a look at 2 points or 2 co-moving observers, and with time the distance will change because of the expansion of the universe or the contraction of the universe, and the scale factor keeps track of that. If the scale factor is 2, after some time, that means the distance between those 2 same co-moving observers will become double after some time. So in this regard, we introduce some terminology. First is the co-moving distance, or sigma, which is a time-independent distance. And it just tells you the co-moving coordinate separation in the co-moving coordinates between those 2 points. As you know, the spatial separation is given by gamma ij. So gamma ij dxi dxj, which is the integral of d sigma, is the sigma. So this is called the co-moving distance, and for 2 co-moving observers, because their spatial coordinates are rho theta phi coordinates are fixed, that sigma will not change. So that I'm going to denote by n equal d sigma. And some people also denote it by r if you take them to be radially located. Because of isotropy, I can choose anything to be my x-axis or y-axis. And then if I use r theta coordinates, then this integral of d sigma will be equal to r as well.